Okay, so now having talked about Voronoi diagrams and Voronoi cells, we're now in a position to talk about the associated Delaunay triangulations. And one often thinks of Delaunay triangulations as being dual in some appropriate sense to Voronoi tessellations. Okay, so the sort of perhaps the best way to think about Delaunay complexes in the context of what we've already learned so far is the following. So the Delaunay complex of a finite set of points in Rd, right, is isomorphic to the nerve, basically. It's like of the Voronoi diagram. Okay, so what I mean by that is that, okay, so if we look at the abstract Delaunay complex, if you will, right, this is just the set of subsets, it's like of this set of points, okay, such that the, you know, common intersection, it's like of the Voronoi cells associated with points in that set, right, is non-empty. Okay. All right. So once we have that, then it's natural to ask whether or not there is a geometric realization of this abstract simplicial complex. Okay. And there is. It's like so long as the points are in some sense what is called in general position. Okay. So we say that. So the set S is in general position. Okay, if no d plus 2 of the points lie on a common d minus 1 sphere. So you might be perhaps familiar with the idea of general position in the context of, it's like things like, linear independence. It's like where if you take the set of points and you choose one distinguished point and you look at the vectors, it's like the direction vectors from the distinguished point to the rest of the points, and there's a linear independence of that, then we say that that's in general position. So more or less, it's like that corresponds to the idea that if you have, a bunch of points, right, that you don't want a situation where, if, for example, you have 2 points, it's like in general, of course, they define a line. It's like you have 3 points in general, they define a plane, right? You don't want a situation where those things end up defining something which is actually, they happen to live on something which is lower dimensional. It's like then the count, it's like would suggest, right? So so something similar happens here. It's like, but instead of just thinking about it in terms of, it's like affine spaces, things like hyperplanes and so on, we're going to look at something a little bit more general. It's like in terms of spheres as well, right? So the same way that, it's like if you have 2 points, it's like you uniquely define a, so say if you have 3 points, you uniquely define, it's like a one sphere, right? You want something, again, where you don't have some sort of, strange degeneracy. It's like, and this is what we call general position. And again, it's a sort of a fairly natural generalization of the notion we have. It's like with hyperplanes, it's like, but now we also include the possibility of living on lower dimensional spheres in some sense. Okay, so and of course this is motivated by the fact that when we discussed Voronoi cells, there's this nice connection, if you will. It's like with sphere inversions and stereographic projections. And again, it's like the fundamental objects there are spheres, and then you can think of the planes, if you will, as being degenerate spheres in some appropriate sense. Okay, so anyway, so the consequence, if you will, it's like of the points being in general position is that this, this Delaunay complex itself, it's like has certain constraints. Okay, so let me state what they are. So this assumption of general position implies that no sort of D plus 2 Voronoi cells have a non-empty common intersection. So another way to sort of think about it is that in general, it's like if you have a Voronoi cell, it is a top-dimensional thing, right? And so what you want is that when you intersect top-dimensional things, it's like the dimension of the intersections, it's like, it's like go down by 1 each time, right? So if you intersect, it's like 2 cells, you should get something which is codimension 1. Intersect something with 3 cells, you should have something which is codimension 2. And of course, it's like if there was this degeneracy, you are not in general position, then it's quite possible that when you intersect 2 Voronoi cells, you get something which is still top dimensional, all right? And then in that situation, you could have non-trivial common intersections with, say, up to D plus 2 Voronoi cells or even more, right? So, so this assumption is fairly natural. It's like also in terms of the intersection, it's like between Voronoi cells. Okay, so the consequence of that assumption that the set of points are in general position is that there are no D plus 2 Voronoi cells. So what with common intersections, non-trivial common intersections, which means that the top-dimensional simplices, top-dimensional abstract simplices in the Delaunay complex, right, are dimension D, right, because they have D plus 1 elements in them. Okay, so this means, so equivalently, right, the dimension of simplices in the Delaunay complex is at most D. Okay, so and that's sort of what we want, right? Because the motivation, it's like, if you will, it's like for studying these Delaunay complexes is that we want to have a simplicial complex associated with a set of points which basically has top dimension, which is at most the dimension of the embedding space. Okay, and if you recall, it's like if you just had sort of a the nerve, it's like of an arbitrary set of sets, right? Then you could have a situation that even though those sets are sets in RD, right, the nerve associated with it could have simplices with dimension graded in D. Okay, so if you will, it's like this whole study of Delaunay complexes is a attempt to try to construct, it's like try to construct complexes with this property that the dimension sort of tops out at the dimension of the embedding space. Okay, so in any case, right, if you have that, if we have points in general position, then the point is that the convex hull of these subsets of the abstract simplices, the convex hull of the simplices of the abstract simplices, is a geometric realization of the Delaunay complex, right? Right, which is referred to as a Delaunay triangulation. Okay. All right. So maybe let's sort of look at a simple example of this just to get a sense as to what's going on. Okay, let's just obviously do this in just two-dimensional space so that we can visualize it. So imagine you have a bunch of points. Okay, let's just see, we have 4 points. Then, if you recall, the Delaunay, I should say that the Voronoi cells associated with this are the intersections of all these half planes, right? So, so let me sort of draw. It's like these half planes. It's like between. It's like all these things. Okay, then there's another one, which is like this. Okay, so, all right. So let's see. So what you might get is, for example, something like this, right? Something like this. Okay, so hypothetically something like that, right? Okay. So this is just a way to partition up. It's like the region, right, into these spaces. Okay, and so actually it's like this is sort of not in general position. What's likely to happen is that you don't have this triple meeting point. You might have something like that, say. Okay, all right. So, so if you were in the general position, it's like then you would only have triple intersections and not higher. Okay, in 2 dimensions. All right. So say you had sort of something like that as your Voronoi diagram. Okay, it's not very precise, but hopefully you get the idea. Okay. So what happens then is that you want to look at the nerve. It's like of this Voronoi diagram. So so let's call this 0, 1, 2, 3. Okay, so you know that 0, 1, and 2's Voronoi cells have a common intersection, which is exactly at this triple point. Okay, so so you know that the simplex associated with 0, 1, 2, right, is in the Delaunay complex. Okay, and it's a complex, so basically all subsets are also included, right? So you also know that 0, 1 is included, 0, 2 is included, and then 1, 2 is included, and then of course it's like 0 on its own, 1 on its own, and 2 on its own. Okay, and then there's of course another sort of top simplex, it's like which is generated by 1, 2, 3. Okay, because again they have a triple intersection here. Okay, so 1, 2, 3 is also there, and then all the edges of that, which is 1, 2, 1, 3, and 2, 3, and then all the vertices, which we already have 0, 1, 2, so the only thing which is left is just 3. Okay, so that would be the Delaunay complex associated with those points. And again, it's like what you do is you have to take these intersection of half planes, and then you get this kind of Voronoi diagram. Okay, and again, it's like if the points are in what is called general position, right, and you're in two-dimensional space, then the maximum intersection you can get, it's like of these Voronoi cells, is up as a sort of like a triple point, okay, which is sort of done here. So hopefully, again, that gives you some idea of what we're talking about when we talk about, it's like Voronoi diagrams, Voronoi cells, and then the associated Delaunay complex and the associated Delaunay triangulation. All right, so actually I'm not, I guess I'm not quite done yet, right? So the Delaunay triangulation then, right, is the convex hull, it's like of the points, right? So you have two top simplices, right? 0, 1, 2, and 0, 2, 3, right? So you have something like this, right? So this would be your Delaunay triangulation, if you will, okay? And then there is some sense in which there is a point at infinity, right? So you then sort of close it all up. It's like by including the point at infinity as well. Okay, so let me just stop here for now, all right, and we'll continue.